find it eventually. There it is. Okay. All right, so we're going to do some review of this second unit here. I'm going to sort of focus on reaction mechanisms in that unit and trying to get better at those reaction mechanisms, specifically reasoning through them rather than trying to like have everything memorized, because at some point you just hit a critical mass. We got too many mechanisms at this point for you to try some memorization strategy, all right? So instead, we want to be able to look at what we're seeing in our balanced chemical equation and reason through what's going to be playing what role, all right? So let's start by reviewing what we talked about with nucleophiles. Nucleophiles were these electron-rich species, right? That's what it means to be a nucleophile, is to have a ton of electron density. And so all of these strong, we made this master list at one point here, all right? But even without frantically copying this down, you have this in your notes, it'll be in a lecture video, all right? If we're trying to spy a strong nucleophile, what does every single one of these have that's going to jump out to us that's going to let us know, yes, this thing is very electron rich? That negative charge, right? So all of our strong nucleophiles, regardless of what atom is holding that negative charge, has a negative charge associated with it. Something that's got to be a dead giveaway for a nucleophile. There were these two neutral ones that we put into this strong nucleophile category. Truthfully, we should probably make a third category of moderate nucleophiles to put those in. But the bottom line is sulfur is a particularly good nucleophile as an atom because it's a lot bigger. It doesn't hold on to its electrons quite as tightly. Nonetheless, 99.9% of it, maybe we have a little asterisk in our mind next to those, but 99.9% of the time, all we're looking out for, is that net negative charge for our nucleophiles, all right? But we can also take all of those strong nucleophiles and protonate them, and that makes these weaker nucleophiles here. How can I spy a weak nucleophile? All right, it's neutral, but what do all my weak nucleophiles still have to have? A lone pair, a pair of electrons, right? A nucleophile has to be able to donate electrons. So even my weak nucleophiles, I can tell that they're weak because they are neutral. But oxygen, every time we see oxygen, we want to be thinking that could be a nucleophile. Nitrogen with its lone pair, that could be a nucleophile, right? So being able to spy these things. And we talked about nucleophiles, but maybe we should have also taken a rewind back to the first semester and talk about electrophiles, because I feel like students are not so great at spying these electrophiles. And our electrophiles are actually a much shorter list than our list of nucleophiles. So it's kind of easier to think about our electrophiles given that sort of short list. So first of all, if nucleophiles are electron rich, what are our electrophiles? Electron poor, electron deficient, whichever one of those you want to use, absolutely. So whereas my nucleophiles, I was looking for negative charges, what about my electrophiles? Cool, yes and no. It's a little bit more complicated than that sometimes. I am looking for electron deficiency, and one amazing electrophile is indeed a carbocation. And I can spy that as an electrophile very easily because it has that net positive charge. All right, but there's something else that our electrophiles need to have. They're electron poor, but they need to be able to accept electrons. And one of the reasons why carbocations are such great electrophiles is because they do not have a complete octet. They can very easily accept electrons. They're begging for that last pair of electrons to complete their octet. So these are great electrophiles because that carbocation has an incomplete octet. All right, so then just for the sake of practice, let's take that good electrophile. We're going to do an example here. All right, right, let's say that I put this thing in with this thing. All right, our first step in sort of predicting our reaction mechanisms is to try to figure out what's going to be playing the role of the nucleophile and what's going to be playing the role of the electrophile. All right, so given these two molecules here, which one do we think is going to play the nucleophile, the left or the right? And why do I know it's that one? Because that negative charge. So here's my nucleophile. My electrophile is going to be that carbocation. Great. Specifically, what's the nucleophilic site over here? Which atom specifically, or which pair of electrons specifically is going to be playing the role of the nucleophile? On what atom? Is it this carbon? No. Is it this carbon? Is it this oxygen? Yes, right? So there's my nucleophilic site. And what's my electrophilic site over here? That carbocation. So in my mind, I'm seeing that this oxygen is glowing red hot with its electron density. This one's got that cold lack of electron density. And what do nucleophiles do to electrophiles? They attack. Nucleophiles attack electrophiles. So I'm going to identify what plays the role of the nucleophile, what plays the role of the electrophile, and I'm going to make sure that my nucleophile attacks my electrophile, which means that the base of the arrow is always going to be at that pair of electrons of my nucleophile, the head of the arrow at that electrophilic site. All right, so in this case here, nucleophile attacks my electrophile. I get this product. Okay, let's take a look at another molecule though. All right, what do we think? This thing is a nucleophile or an electrophile? An electrophile, what gave it away? The positive charge. All right, but what's my electrophilic site on this molecule? So, sort of might be tempted to say this oxygen here, right? But let's take one of our nucleophiles with its electron density. If this thing attempts to attack this oxygen, yes, that oxygen has a positive charge. But if I do this out, that's a bond formation arrow. I'm going to get something like this. And this should make everybody's organic chemistry brain explode here, because what's wrong with this oxygen? It broke the octet rule. It's got too many electrons. All right? So, yes, this oxygen is positively charged. This is a molecule that has a relative lack of electron density. But I can't possibly attack that positively charged oxygen without breaking its octet rule. Again, one of the most important features of an electrophile is its ability to accept electrons, and that oxygen cannot accept electrons. So a lot of our electrophiles, a carbocation being kind of the exception because of its incomplete octet, a lot of our electrophiles fall into this category of molecules that have good leaving groups. So in this molecule here, the hydrogen is going to be my electrophilic site, meaning that's what's going to get attacked by that negatively charged nucleophile. The other half of this molecule is going to be playing the role of a leaving group. It's going to get kicked off when that hydrogen gets attacked. So that pair of electrons comes and attacks that hydrogen, kicks off that water molecule as a leaving group. It's a good leaving group because it's neutral, nice and stable. In this case, I just form another water molecule. All right, but there are several electrophiles where they have this site that has relative electron deficiency, but they have this good leaving group. Okay, so first of all, we're going to look at this, and again, it's kind of a short list, so we can kind of just build out this list here. One example would be an acid, so HA. My electrophilic site is that proton. But that conjugate base is playing the role of a leaving group. Right? We say acids donate their protons. That means that the other half gets kicked off as that leaving group. Okay? There's another molecule that we see, or another functional group that we commonly see playing the role of the electrophile, and those are our alkyl halides. Super relevant for this chapter because we talked about converting alcohols to alkyl halides to make them better electrophiles. So in this molecule here, I want everybody to identify the electrophilic site and identify what our leaving group is. All right, so where's my electrophilic site? Where's that relative lack of electron density? My carbon that's bonded to my bromine. Remember, this is this polar bond. So that means that carbon has that relative lack of electron density. That bromine is then going to play the role of the leaving group in this molecule. All right, well then what about alcohols? Alcohols, oxygen's also very electronegative. It's even more electronegative than bromine, actually. So I also have this polar bond here. Why do we not consider alcohols to be electrophiles, though? This does have this lack of electron density, but what is it missing? The leaving group, right? This is not a leaving group. So that is why alcohols are not electrophiles. Yes, they have that same polar bond. They have that same carbon with that lack of electron density, but they don't have that good leaving group built in there. We did have a strategy for turning an alcohol into a better leaving group. What was that? We could just turn it into an alkyl halide, but there was another simpler strategy. Protonate it, right? If we add an extra hydrogen to it, now all of a sudden it has that positive charge. So a protonated alcohol, this has got a very good leaving group on it, and it can play the role of that electrophile, right? But again, we have to have that lack of electron density, but we also have to have a good leaving group so that we can actually attack it and not ruin anybody's octet. There's one other functional group that we see playing the role of an electrophile a lot, and this is going to be especially important next chapter, or rather next unit, because we're going to focus on these carbonyl-containing compounds. So everybody take a second, identify your electrophilic site and your leaving group. All right, where's that relative lack of electron density? Where's my electrophilic site? That carbonyl carbon, right? Because again, we got this polar bond. But then where's my leaving group? This is a little bit weird. Our leaving group is when that carbonyl carbon gets attacked. Our leaving group is just that pair of electrons in that pi bond that's going to get kicked up onto that oxygen. So my leaving group here is my pi bond in this particular functional group. All right, so carbonyls. Okay, so we do have our positively charged carbocations that are great electrons. Those carbocations can accept pairs of electrons because they have an incomplete octet. Most of our electrophiles, though, they need, yes, that electrophilic site, but they also need a good leaving group that's built in there as well, all right? But given any sort of a reaction, if I'm trying to figure out, if I'm trying to reason through what my reaction mechanism is, I want to figure out what conditions I'm under, acidic or basic, so I know what charges are allowed. But then I'm also going to try to just identify what's my nucleophile and what's my electrophile in that step. So then let's take this and apply it to this chapter here. All right. We have alkenes in the presence of dilute sulfuric acid. If I'm given this here, how do I know this means dilute sulfuric acid? What's the giveaway? Because there's water there, right? So I mixed sulfuric acid and water together. I diluted that sulfuric acid. So everybody take a second, see if you can't tell me what the product is of this reaction, and then we're going to go through and look at the mechanism of this reaction. All right, so first of all, if I'm having trouble, if I get to the exam and I'm like blanking on what I'm supposed to be putting here, it's probably a good idea to just take stock of what it is that we were studying for this exam, right? What functional groups have we just covered in this particular unit? Let's think about it. Someone yell one out. What's a functional group that we covered in Unit 2? Alcohol. So we covered alcohols. What else did we cover? Ethers, epoxides. So alkenes we used as substrates, but they weren't like one of the main features. So yes, we're definitely going to talk about alkenes, but we featured these functional groups here. There were two more, the thiols and the sulfides. So basically, I'm on an exam and I get to this problem. I'm going to be pretty confident that at least one of these functional groups is probably going to show up in my product here. All right, so just kind of remembering. I just remember in organic chemistry, sometimes I would get really intimidated, like they just expect me to know every reaction of everything, right? And no, we put things into little categories for a reason. So this particular category were these functional groups that we learned together. So yes, we're going to be using one of these as our product. What is the functional group in this case? So this is an alcohol. Okay, we're going to do an addition reaction. That's what alkenes undergo. We do have to remember what's called the regioselectivity of this reaction, which is which one of these carbons, the orange or the green, is going to get that alcohol group. Our more substituted carbon that orange one. All right, so then why is that? Because you don't want to just have this memorized that this is going to be this way. We want to turn to our reaction mechanism to understand why we have that specific regioselectivity. Right? Why is that particular region of our molecule, our more substituted carbon, where that new bond is going to be formed? Okay? So step one, we're going to identify what our reaction mechanism is, what conditions rather we're under here. Is this an acidic or a basic conditions mechanism? So this is an acidic conditions mechanism, and how do I know it's acidic? What's the giveaway? Sulfuric acid, right? If you're reading your list of reagents and you say the word acid, you can be confident that those are acidic conditions. So we can have no strong bases. And a cheat for looking out for that are no negative charges, right? There are some exceptions of things like bromide ions, sulfate ions that have negative charges that are not strong bases, but nonetheless, this is a very easy thing to look out for to make sure our mechanism's correct. Okay. Our alkenes, maybe we can go back and add that to our list here of weak nucleophiles. But alkenes are weak nucleophiles. Specifically that pi bond. All right, our pi bond can play the role of a nucleophile. When we were talking about alkenes in the first semester, it's because of the geometry of our alkenes. They're flat at that double bond region. They're that trigonal planar geometry. They're also those weird pi bonds, so they extend above and below that molecule. They're just a really accessible pair of electrons. So they're going to play the role of our nucleophile. And then let's look here at our reagents. We're trying to figure out what our electrophile is. Is it going to be water or our sulfuric acid here? Right? Which ones are electrophiles? Is water an electrophile? No, it's in fact that weak nucleophile. Remember, our acids are electrophiles because they have that built-in good leaving group there. All right? Now, this is, so if you said that our acid was H2SO4, I would let you get away with it. All right? Truthfully, since this is dilute sulfuric acid, we have to remember back to general chemistry. What's going to happen when we put that strong acid in water? 100% of it will dissociate because it's a strong acid into what's called hydrogen sulfate and hydronium. So you don't actually have any sulfuric acid molecules left over floating around in solution. So again, I'd give it to you if you said sulfuric acid, but really since it's dilute sulfuric acid, the one that would be strictly correct, the one that you would see in every textbook, would be those hydronium ions, right? Because that's what's going to be forming in this dilute sulfuric acid. If there wasn't water present, then you could use just H2SO4, but again, I would let it slide here. So then let's do our reaction mechanisms, starting out with our nucleophile. We've established that the acid is going to be our electrophile. So then everybody's going to take a second and do our first step in our mechanism. Because what do nucleophiles do to electrophiles? Attack. right, so our nucleophile is going to attack our electrophile. We kick off that conjugate base, that water, as a leaving group. All right, but this is one of those bond breaking and formation arrows. So what is my organic intermediate going to be here? We have a special name for this intermediate. I haven't finished drawing it yet. Something's missing. That carbocation intermediate, which is why this reaction has that regiospecificity, because that carbocation is specifically going to form on that more substituted carbon. All right, so we get a bond breaking, our carbon-carbon bond breaks, and a bond formation, our carbon-hydrogen bond breaks. Our other carbon has to get that carbocation. All right, so now in our next step, we're going to look. That carbocation is going to play which role? Electrophile or nucleophile? Electrophile. So then take a second, given what's in our reaction mixture here, identify what your nucleophile should be. All right, is it going to be the sulfuric acid? No, that's an acid. Those are electrophiles. Is it going to be the water? Yes, that's our weak nucleophile. So then if this is our nucleophile, and this is our electrophile, everybody, what do nucleophiles do to electrophiles? Attack. So let's do that. My nucleophile is going to attack my electrophile. Okay, if I look at this thing here, all right, this might be a little tricky because we looked at this and we said that this was a good leaving group. But if we kick this off as a good leaving group, where does that take us? Right back to where we were, right? Now we're just right back to that carbocation. So in order to figure out what my productive step forward is going to be, it's always helpful to draw your product first before you get started with your mechanism, so you have an idea of where you're going. What are we going to need to do to accomplish this last step in our mechanism? We're going to need to deprotonate that alcohol group, which means that we need a base. And what's going to play the role of a base under these acidic conditions? That water. If you did HSO4, that would be fine. You'd be reforming that acid catalyst. From like a balanced chemical equation standpoint, it's not wrong. However, if we think about what's floating around in this solution, one of these is a much stronger base than the other one, and that is water, right? What makes sulfuric acid such a strong acid is the fact that this thing is nice and stable all by itself. It's an absolute trash base. So really the water, again, if you did it on an exam, I would let you get away with it. But if we're thinking about what's strictly going to happen in solution here, it would be those water molecules. Right, so now we'll have another water come along, play the role of the base, and give us our alcohol product. All right, so we want to try to, as best we can, reason through and understand our mechanisms for whenever we're drawing them out, because it's just too much information to try to memorize. You're not going to have this memorized what arrow to put where. You want to look and be like, okay, well, there's the electron density. That should be my nucleophile. Okay, there's the lack of electron density. That should be my electrophile. That's ideally what connection we're making here. All right, so we said that we could go this direction, what was called a hydration reaction. This was what was called a hydration reaction, where we use that dilute sulfuric acid and water, and we don't have any temperature specification here, right? This took place at room temperature. We get this alcohol product that forms. But we also said that we could go the exact reverse direction as well, what's called a dehydration reaction. And this was like very similar but subtly different conditions here. First of all, instead of using dilute sulfuric acid, I used concentrated sulfuric acid, H2SO4, so no water in there. All right. The other big difference was that I need to use high heat in order to promote this reverse direction reaction. All right. The reason for this, we said, was we have these two components to whether or not something occurs. The delta G of our reaction. Delta G equals delta H minus T delta S. Well, a hydration reaction is enthalpically favorable. Turns out that breaking that carbon-carbon bond and replacing it with a carbon-oxygen, carbon-hydrogen bond yields a lot of energy, releases a lot of energy, right? These bonds over here are more favorable than these bonds over here. Alkenes are great starting points in a synthesis reaction because they're actually pretty high energy. It does not take very much to break a carbon-carbon double bond, right? So if I want to go back the other direction, I have to take advantage of the other component of delta G, the delta S. And when we're doing a dehydration reaction, we're taking something big and complicated and breaking it into two smaller parts. So this would be favorable from an entropy standpoint. And since that enthalpy term, or rather entropy term, scales with temperature, the larger the temperature, the more that delta S is important, right? So that's why at high heat, I have that reaction going in this direction, whereas low temperatures, it's going to go towards my more favorable bonding product by alcohols, all right? So we can get our reaction to go in this direction if we use that high heat. So let's see if we can't do our mechanism for the reverse direction. Let's actually just real quick do our chemical equations so we can see things a little bit more clearly. All right, so first of all, conditions. Step one, figure out what our conditions are. Acidic or basic? Everybody take a second. See if you can't figure this out based on our chemical equation here. Right, so what's giving it away that this is acidic conditions? The sulfuric acid. So again, we are under these acidic conditions. All right, we have our alcohol here. Is your alcohol going to be a nucleophile or an electrophile? Why is it going to be a nucleophile? Because my acid's the electrophile, definitely. And what gives it away that this is a nucleophile again, structurally? That lone pair. So alcohols are definitely on our list of our weak oxygen nucleophiles, right? They're the protonated version of those alkoxide ions. So this is going to be our nucleophile. And what was our electrophile going to be? The acid. And in this case, since I don't have any water present, I am going to use that H2SO4. So yep, acids are our electrophiles. I'm going to be lazy and not do my full Lewis structure here. Kind of use this abbreviated version. But this is my electrophile. And what do nucleophiles do to electrophiles? Attack. All right, so everybody take a second. Do my next step in my mechanism here, rather draw me my intermediate. Right? So now we get to this point here where we have that protonated alcohol group. And this thing should jump out to you as looking a little weird, right? We have that positively charged oxygen. What is this thing right here? What do we know about these protonated alcohol groups? What role do they like to play in our reactions? Leaving groups, all right? Now, normally or often, there's some some nucleophile will attack in order to kick off this leaving group. But in this case, we're at that high heat, right? So because of that high temperature, breaking this molecule into these two components is that much more favorable. And so because of that high heat, we're just going to kick off that leaving group. All right, so high heat, so our leaving group leaves. Okay, our leaving group is going to leave as that neutral water molecule. What's my intermediate missing here? Yep, that carbocation, positive charge. All right, and this is kind of the trickiest step in this whole thing. Again, where are we going? We're forming an alkene. All right, and this is what I'm going to have kind of like starred in the back of my brain as kind of the more difficult aspect, the less obvious aspect of this particular mechanism, is that it's going to have to involve the neighboring carbon. All right, so why is that? Let's fill in our implied hydrogens over here. How many hydrogens do we have? 3. And let's fill in our implied hydrogens on that same carbon over here. How many does it have? Only 2. So the hydrogen on this carbon is going to have to be involved in this last step of my reaction. One of the hydrogens. There's 2 of them that won't be involved, but one of them will be. All right, I got to remove that hydrogen, and I got to form my carbon-carbon double bond. All right, where is this pair of electrons going to come from in my carbon-carbon double bond? Where is that in the previous step? That carbon-hydrogen bond. All right, so we need to remove that hydrogen, meaning we need a base. Whoops. And what base are we going to use under these acidic conditions? Yeah, so we got two candidates here, kind of just like we saw in the previous example, that HSO4 minus or H2O, but water is the correct choice here. That is the stronger of the two bases. So the water that I just formed is going to turn around and play the role of the base, deprotonating that carbon and allowing that pair of electrons to come down and form my pi bond. Created some hydronium in the process. All right, so again, just trying to reason through our reaction mechanisms as much as we can here. Rather than having it be a full-blown memorization process, making sure that we can see at each step what is going to play the role of the nucleophile, what is going to play the role of the electrophile. All right. One more reaction just to kind of have next to these in our notes because they're very similar. We had this dehydration reaction at high heat to form an alkene. In the next chapter, we learned about another dehydration reaction. So this is plus water, that's why it's a dehydration reaction. And this was very similar, yet subtly different here, because instead of having high heat and concentrated sulfuric acid, I had moderate heat and sulfuric acid. Right, whereas this dehydration converted my alcohol to an alkene. If we use instead moderate heat, we're going to get alcohols being converted into ethers. So everybody take a second and draw me my ether product for this reaction here. So in this situation here, we don't have quite high enough heat. We actually form the same intermediate here, but we don't have high enough heat to just kick off that leaving group without an electrophilic attack. Instead, an electrophile is going to attack, kicking off that leaving group. And our electrophile is, a nucleophile is going to attack, kicking off that leaving group. And our nucleophile is a second molecule of that alcohol. So in this reaction here, we end up forming those symmetric ethers and water. All right, and what I want you to do for your studying this afternoon is to do the reaction mechanism for this and compare it and contrast it to our previous mechanism. And you'll note that the difference is at this step right here. Instead of having our leaving group just fall off because we have high heat, so it will promote breaking that big molecule up into those two smaller molecules, we're going to have a nucleophile that attacks and kicks off that leaving group. And that's how we connect those two molecules together. All right, but these are very similar, so having them next to each other in your notes is going to be very helpful. All right, we'll pick up next time and do some more review. What's up?
I have a question. The homework that was due last night, I was having a lot of difficulty, not with the end product, because I could get to that point. It was with the formation of the stereochemistry of like the epoxy.
Okay.
So like I was just having difficulty with like the dashes and wedges on